Welcome back. In the last video, we created our own Transformer Encoder block. And we combined the code we wrote for equation 2 and equation 3, put it together in a forward method, added the residual and skip connections, and then we got a summary output of what it looks like for an image or a sequence of image patch embeddings to go through a single Transformer Encoder block. And we know that from the paper, there's actually multiple Transformer Encoder blocks. And this large L here is in table 1, if we go down to there. So VIT base actually has 12 of these layers stacked on top of each other. So that's something we're going to be doing later on when we construct everything into the VIT base architecture. But for now, let's just jump into the keynote and get a little bit of a colorful mapping of what we've done. So we've got the MSA equation 2, the MSA block. We wrote this code before. Then we've got the MLP block, which is these two layers here, and we've got that there. And then we've got the residual connections down the bottom here for each block. But that is the Transformer Encoder. And I said that I was going to reveal a little trick that we can do with PyTorch to make everything that we've done so far, well, not everything, but a fair bit of it, namely equation 2, 3, and the Transformer Encoder, even smaller than this little block of code. So let's see that in action, hey? So I'm going to create this 7.2, which will be, are we up to 7.2? Maybe I'll call this 7.1. So this was 7.1, 7.1, create a custom, oh, you'll see why, create a custom Transformer Encoder block. Wonderful. We X out of that. And now in here, 7.2 is going to be create a Transformer Encoder, well, PyTorch call it a layer, Transformer Encoder Layer with inbuilt PyTorch layers. Now, if you've got a keen eye for the PyTorch documentation, you might have seen that PyTorch has transformer layers. Transformer. And if we go torch.nn, transformer layers. So I'm going to just copy this here. So far we've created a Transformer Encoder by hand. But because of how good the Transformer architecture is, PyTorch has implemented ready-to-use Transformer Encoder layers. And that's where we can find it here. And you remember how I said there's decoders as well? Well, we've got the option to use a decoder, but there's an overall transformer model, which is what we're working towards, a vision transformer. There's a Transformer Encoder, is a stack of N encoder layers, which is very similar. I might just get out of a few of these tabs. I don't think we need this anymore. Which is very similar to what we've got over here. Transformer Encoder, which is a stack of these blocks here. So that's what we're reading there. Transformer Encoder is a stack of N encoder layers. And then we have here, nn.transformer encoder layer is made up of self-attention, which is what we've done, and a feed-forward network, which is another word for MLP. As I've said, there's a lot of different names for the same thing in deep learning. But let's jump into this. So Transformer Encoder Layer is made up of self-attention and feed-forward network. This standard encoder layer is based on the paper Attention is All You Need, which is where the VIT paper has based their architecture on. Beautiful. So what else is here? Oh, okay, so that's just telling us where it's from. So we can modify or implement in a different way during application. So let's just try to see how this goes, hey? So we've got some parameters for D model, which is the embedding size, number of heads, which would assumingly be the multi-head attention, how many heads there is, dim feed forward, maybe this is the number of hidden units in the MLP, and there's dropout, and there's the activation function. Oh my gosh, it looks like we've got all the parameters that we use to create our own transformer and block. So how about we see what it's like to create this with PyTorch. So we can create a Transformer Encoder Layer with pure PyTorch layers. So let's see if we can replicate our above custom implementation with pure PyTorch. Create the same as above with torch.nn.transformer encoder layer, which is just this layer here. So let's see what this looks like. Torch transformer encoder layer equals nn.transformer encoder layer. And then what do we get? Do we get a doc string here? Yes, we do. Dmodel, this is going to be our embedding dimension. So I might just put that as hard-coded that. So this is embedding size from table 1. Then we'll go to the next. N head is going to be what? For vit base is number of heads. So heads from table 1. And then what else do we have? Dim feed forward, which in our terminology is MLP size. So this is going to be 3072. So we'll go, this is MLP size from table 1. Then what else do we have? Well, we have dropout. So dropout is going to be 0.1. Well, it's already 0.1 by default there. And then we go next. We want activation. So we can set this as a string to Jelu. Now, how do I know that? Well, if you jump into the documentation, we have activation. The activation function of the intermediate layer can be a string, relu or jello, or a unary callable. So we're just going to use Jelu because that's what we've used in our implementation. If we come up here, we used nn.jelu. And so if we keep going, batch first, if true, the default is false. So what are we using? We're using batch first. So we'll just come back down to where we were. Next thing is batch first. So our batch dimension is coming first, true. And then the final thing is we have norm first. So norm first. Did we do our normalization layer first? So let's jump back into the paper. We have normalization first in this case. So in here we have if true, layer norm is done prior to attention and feed forward operations respectively. Otherwise it's done after. So the default is false to come after. So we want it to happen before if we're replicating the vision transformer. The reason why it's by default on false is because if you go into this paper, I believe their architecture, the original transformer, did it after. So this is the original transformer encoder. Now if we compare, they've just switched these around. Now I'm not 100% sure behind the reasoning of that, but in our case, we're focusing on replicating VIT. So it's not too dramatic of a change. We're just doing one layer after the other. We're just mixing the order around. So I think that's enough to replicate what we've just built here. But behind the scenes, this is also implementing equation 2 and 3 and turning it into an encoder for us, all with just this code here. So let's compare. Let's just see an output of this. Torch transformer encoder layer. And then how about we get a summary? Okay, we've got multi-head attention. We've got a linear layer. We've got dropout, linear, layer norm, dropout, dropout. We'll get a summary of the output here. So in this case, instead of transformer encoder block, we want it to be torch transformer encoder layer, which is PyTorch's implementation. Torch transformer encoder layer. Let's see how it compares to our own. Wonderful. So the ordering here looks a little bit different to what we've got because we've created ours with series of blocks, but it looks like the PyTorch implementation might just be a straightforward sequential version. But if we look at the number of parameters here, 7,087,872 is the same as, beautiful, ours has got the same number of parameters here as well. But it also looks like their estimated forward pass size might be smaller. But we've still got the same operations happening behind the scenes. And so yeah, hold on, Daniel. If we can create a transformer encoder layer, why did we spend all this time replicating equation 2, 3, and then putting them together for the transformer encoder block? Well, I'm going to come clean. I knew that we could create it using this transformer encoder layer the whole time. but I wanted to replicate them with our own custom blocks so that we could see what it's like replicating equations straight from a paper in full completeness. So we could practice what it's like. And now that you've seen how to replicate single equations into single blocks of PyTorch code, when you call something like this, you can infer what's going on behind the scenes. And if you come across another paper that implements a slightly different version of a Transformer Encoder Layer, well, you can manipulate the equations here that we've created with code to suit your liking. So that's the whole point of practicing replicating a paper from scratch, is we start with the simplest implementation, and then we can adjust it if needed. And if we find a quicker way to do it, well, we can do that with direct PyTorch layers, but at least we now know what's happening behind the scenes. So finally, let's just make this concrete. I'll just write this down. Why spend all this time recreating the Transformer Encoder when we could have just made it with a single PyTorch layer? Practice. 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 Now we know how things are implemented behind the scenes. We can tweak them if necessary. So, what are the benefits, you might be asking, of using a pre-built PyTorch layer? Well, number one is going to be less prone to errors. So every layer that goes into the PyTorch library goes through a bunch of testing, whereas if we just coded everything like we have from scratch, unless we've used it a few times, it looks like it works, but it might not behind the scenes. And then also we have a potential benefit of speed ups, so performance boosts. So I'll just jump into the book version of the course, PyTorch paper replicating. And if we go down to here, this is where we're at, creating a Transformer Encoder Layer with PyTorch's Transformer layers. Here we go. The benefits of using the pre-built PyTorch layers, such as less prone to errors and a potentially better performance. So as of July 2022 and the release of PyTorch 1.12, if you use the PyTorch version, implemented version of Transformer Encoder Layer with a specific setup, so this is in the documentation too. Yeah, here we go. Fast path. Ford will use a special optimized implementation if all of the following conditions are met. So I'll let you read through those as extra curriculum, but this is one of the major benefits of using a pre-built PyTorch layer, is that if we click on this blog post, this is fairly recent at the time of recording, so I'm recording this video in August 2022, but through the middle of July, PyTorch released a better transformer for fast transformer inference. And what it's saying is, yeah, launching with PyTorch 1.12, Better Transformer implements a backwards compatible fast path of Torch NN Transformer Encoder for Transformer Encoder inference and does not require model authors to modify their models. So Better Transformer improvements can exceed 2x speed up and throughput for many common execution scenarios. So what this is essentially saying is if you use the PyTorch implementation of the transformer layers in a specific setup, you can benefit from faster inference time. And there we go. Hey, that looks a lot like what we've just created, except this is the attention is all you need version here. We've just swapped it around for the Vision Transformer version. So I'll let you read that as extra curriculum, the documentation for the transformer layers. And I'll get out of that. You can see that in torch.nn. And then there's also a blog post here that I've linked in the book version of the course under 7.2, where you can read up how PyTorch enables a potential speed up if you use their inbuilt transformer encoder layers. So with that being said, there's one more note here. If you wanted to stack together these transformer encoder layers, there is the Transformer Encoder, where you can pass in the encoder layer that you created and the number of layers. So in the case of the vid architecture, the number of layers here would be L times whatever you want. And the hyperparameters are in table 1. So in our case, it would be, if we come back, num layers equals 12. So just keep that in mind. A fair bit of extra material to go through, but nothing you can't handle. We've just now created a transformer encoder with our own custom code and with inbuilt PyTorch layers. So now I think we've got all the pieces of the puzzle to put together the entire architecture. So if we go back, well, we've got this in code, we've got this in code, we've got this in code, and we've got all of this in code. We're just missing this. I think we can do this all in one hit. So if you're with me, I'll see you in the next video. We're going to start to create the entire vision transformer. I'll see you there.